look at graphing of linear motion, Giancoli 2.8. So here's a position time graph, and we made one of these earlier in the year, but you can see it's a straight line. If we want to find the velocity in a position time graph, all we have to do is find the slope, and we can pick 2 points and do point slope form, rise over run. I mean, obviously, if we do this on a graphing program, we can find slope using the program, but just understand, on a position time graph, the slope, all right, the slope will tell us the velocity. Now here's a position time graph with a varying slope. So we're speeding up, slowing down, changing direction, doing all kinds of stuff. If we wanted to find like the average velocity between two situations, between T1 and T2, we just draw, right, a line and then find the slope of that line. So essentially we're just going to pick 2 points and again use point slope form, and we can find the slope, and that will tell us the average velocity during that time interval without needing to see a straight line on the graph, which is what we can do. Same one before, right? So now we want to see interval T3 to T1, right? And we see that the average velocity between T3 and T1 is different than the average velocity between T2 and T1. If we pick a point on the line and draw a tangent, if we find the slope of that tangent line, that is called the instantaneous velocity, all right? So we can find the average velocity using 2 points and point slope form. If we want to find the actual velocity at any given point, that's where we have to draw a tangent to our curve and then find the slope of our tangent, and that will be the velocity at that time exactly. Not the average, the instantaneous velocity. So same curve, okay, that we've seen, but now we find the slope at 4 different points. So the slope here, small but positive. Here, way increased and positive, so speeding up, right? Then we get to this point and it's flat, which means at this point the object is not moving, probably changing direction. If I look at this, so it's going to stop and change direction. And then we have a negative because we're going back in the negative direction, so the velocity will be a negative velocity, negative slope. But we can find all kinds of information from this curve. It's not just saying, okay, this object is going to speed up, stop, and then turn back and go back in the negative direction. We could talk about it that way, but at the end of the day, we could find slopes at all these points and see the velocity at those points. So now velocity time graph. A velocity time graph, if we find the slope of that will tell us the acceleration. So we can do the same thing, right? If our velocity varies, we can see that here we have a slope and here we have a slope, right? But this can be P1, since it's a slope of a tangent line, is the slope of is the instantaneous acceleration. While if I look here, this is the average acceleration because I have 2 points. So again, the tangent line tells us instantaneous acceleration, but if I use 2 points, that's going to be the average acceleration. But the slope of a velocity time graph is the acceleration. So we look here. In this figure, we see 2 cars, A and B, and we want to find the average acceleration. So I'll just pick the 2 points, the starting point, ending point, 0 to 100 in 10 seconds. Both of these have the same average acceleration because they both start and stop at the same point. The instantaneous acceleration would be the slope at any of these given times, and you can kind of see that car A will have a steeper slope here, so it'll have a greater instantaneous acceleration initially, and then as it gets flatter, car B will have a little bit more instantaneous acceleration. So like if we were describing the motion of car A, we would say it really accelerates quickly and then slows down to the point where it reaches the 100 kilometers per hour. Car B accelerates at a more constant pace. It still accelerates, it's still curved, but it's going to be more of a constant pace as opposed to a really quick acceleration that we see in car A. But now total distance traveled. If I have a velocity time graph, the total distance traveled would be the area under the curve. So I look at car B, all the area under this curve would be the total distance traveled. Car A would have this all of B and then plus this area here, which means car A traveled more distance than car B. So to rehash, position time graph, The slope of a position time graph tells us the velocity, and we can find instantaneous or average. Instantaneous would be a tangent line, and average would be the 2-point slope form. If we have a velocity time graph, the slope would be the acceleration. But then if we find the area under the curve of a velocity time graph, that will tell us the total distance traveled. And that's information we can get from these graphs.